In March 2024, astronomers confirmed something that should be impossible. A galaxy so distant, so ancient, that according to our best models of the universe, it simply cannot exist. This isn't about finding something unexpected. This is about finding something that violates the fundamental laws we use to understand reality itself. The galaxy, catalogued as JWST Z14-0, is shining at us from just 290 million years after the Big Bang. To put that in perspective, the universe hadn't even cleared the fog yet. Stars shouldn't exist. Galaxies definitely shouldn't exist. But there it is, blazing in JWST's infrared eyes, demanding an explanation we don't have. What you're about to hear will challenge everything you thought you knew about cosmic evolution. We're going to trace the trail of impossible galaxies that led to this moment, examine why this discovery terrifies physicists, and explore what it means when the universe refuses to follow its own rules. Because JWST Z14-0 isn't alone, it's part of a pattern. And that pattern is forcing us to confront a disturbing possibility, that our entire understanding of how the universe began might be fundamentally wrong. Before we dive into why this galaxy breaks physics, you need to understand what made it possible to see in the first place. And that story begins not with a telescope, but with a problem that haunted astronomers for decades. For most of human history, looking deeper into space meant looking further back in time. Simple enough, light travels at a fixed speed. When you see a star tens light years away, you're seeing it as it was 10 years ago. Scale that up to billions of light years, and you're essentially building a time machine that only works in one direction, backwards. But there was always a horizon we couldn't cross, a boundary beyond which the universe went dark. Not because nothing was there, but because we didn't have the right eyes to see it. That horizon sat at roughly 13.4 billion years into the past, a record held stubbornly by a galaxy called GNZ11, discovered by the Hubble Space Telescope in 2016. GNZ11 represented the limit of what optical astronomy could achieve. Hubble, with its 2.4-meter mirror, had pushed human vision to extraordinary depths, but it was fundamentally constrained by the same problem that limits all optical telescopes: the expansion of the universe itself. Here's why that matters. When light travels through expanding space, it gets stretched. The wavelengths grow longer, shifting from blue to red, then beyond red into infrared territory that human eyes can't perceive. This is redshift, and it's measured on a scale where higher numbers mean older, more distant light. GNZ11 had a redshift of 11.1. To see anything further, you'd need a telescope that could detect deeply infrared wavelengths with extraordinary sensitivity. Enter the James Webb Space Telescope. Launched on Christmas Day 2021, after decades of delays and cost overruns that made it NASA's most expensive science mission ever, JWST was built for exactly this purpose. Its 6.5-meter mirror, plated in gold to optimize infrared reflection, was designed to capture the stretched, ancient light from the universe's first galaxies, the kind of light that Hubble could barely glimpse. When JWST opened its infrared eyes in July 2022, astronomers expected to find a handful of early galaxies, small, faint, primitive things forming slowly in the cosmic dawn. Time one bis. What they found instead was chaos. The first deep field images revealed dozens of galaxies that shouldn't exist yet. Bright, massive, structured galaxies appearing far earlier than any model predicted. It was as if JWST had discovered a fully formed city in a timeline when humans should still be learning to make fire. Within months, the telescope had shattered Hubble's distance record not once, but repeatedly. First came JWST Z13-0, pushing back to a redshift of 13.2. Then JWST Z14-0 emerged from the data, clocking in at a redshift of 14.32, corresponding to just 290 million years after the Big Bang. But the redshift was only the beginning of the problem. The real trouble started when astronomers analyzed what they were actually looking at. This galaxy is compact, only about 600 light years across. For comparison, that's roughly the distance from Earth to the nearest star cluster, the Pleiades. Our Milky Way spans 100,000 light years. JWST Z14-0 could fit inside a single spiral arm of our galaxy with room to spare. Yet despite its tiny size, it's astonishingly bright, pumping out light equivalent to hundreds of millions of young, hot stars all burning simultaneously. That shouldn't be possible. Not yet, not this early. To understand why this galaxy terrifies cosmologists, we need to talk about what the universe was actually like 290 million years after its birth. And I promise you, it's far stranger than you imagine. The universe at 290 million years old was nothing like the cosmos we see today. To grasp why JWST Z14-0's existence is so profoundly troubling, you need to understand the conditions that prevailed in this era, a period astronomers call the Cosmic Dark Ages. The name is fitting. For hundreds of millions of years after the Big Bang, the universe was literally dark. Not dark because light didn't exist, but dark because light couldn't travel. The entire cosmos was filled with a dense fog of hydrogen atoms, and that fog was opaque to visible light. Imagine trying to see through a wall of steam so thick that even the brightest flashlight becomes invisible at arm's length. That was the universe. This fog wasn't some minor inconvenience. It was a fundamental barrier that shaped everything about how the early universe evolved. When the Big Bang occurred 13.8 billion years ago, the universe was unimaginably hot and dense. So hot that atoms couldn't even form. Electrons and protons existed as a plasma, a superheated soup of particles that scattered light in every direction. Photons couldn't travel more than a tiny fraction of space before bouncing off another particle. As the universe expanded, it cooled. Around 380,000 years after the Big Bang, something critical happened. The temperature dropped enough for electrons and protons to combine into neutral hydrogen atoms. This moment, called recombination, is when the universe became transparent for the first time. The cosmic fog cleared, and light could finally travel freely through space. That light is what we detect today as the cosmic microwave background radiation, the faint afterglow of the Big Bang visible in every direction we look. It's the oldest light we can see, a baby picture of the universe taken when it was less than 500,000 years old. But here's the critical point. After recombination, the universe fell back into darkness. Why? Because there were no stars yet. The hydrogen, atoms that filled space, were neutral, not ionized. And neutral hydrogen absorbs ultraviolet and visible light, creating a fog that blocked any light sources that might have existed. The universe had gone from opaque plasma to transparent gas and back to opaque fog, all within a few 100,000 years. This is the era that JWST Z14-0 was born into, an epoch where the universe should have been dark, quiet, and simple. Just vast clouds of hydrogen and helium slowly collapsing under their own gravity, beginning the gradual process of forming the first stars. According to our models, this process should have taken time, a lot of time. The first stars, called population 3 stars, were predicted to be massive solitary giants forming in isolation from the sparse gas clouds that existed back then. These stars would have been short-lived, burning through their fuel in just a few million years before exploding as supernovas. Only then would they seed the universe with heavier elements needed for the next generation of stars. Galaxies were supposed to form slowly through a process called hierarchical assembly. Small clumps of dark matter would pull in gas, forming tiny proto-galaxies. These would merge over hundreds of millions of years, gradually building up into larger structures. The first galaxies should have been small, dim, and chemically simple, composed almost entirely of hydrogen and helium with barely a trace of heavier elements. The timeline was clear. The universe at 290 million years should have been in the early stages of this process. Maybe a few primitive galaxies, certainly nothing bright or complex. The epoch of reionization, when enough stars formed to burn away the cosmic fog and make the universe transparent again, wasn't supposed to begin until at least 400 to 500 million years after the Big Bang. But JWST Z14-0 throws all of that into question. This galaxy isn't small or dim, it's not chemically simple. When astronomers analyzed its light using JWST's spectroscopic instruments, they found something shocking. The galaxy's spectrum shows clear signs of oxygen, carbon, and nitrogen, heavy elements that can only be created inside stars through nuclear fusion. The presence of these elements means that multiple generations of stars must have already lived and died before JWST Z even formed. Stars had to be born, fuse lighter elements into heavier ones, then explode as supernovas to scatter those elements back into space. Then those enriched gas clouds had to collapse again, forming new stars with higher metallicity. This is a process that should take hundreds of millions of years, not the cosmic eye blink that had passed since the Big Bang. Think about what this implies. At just 290 million years, the universe hadn't even had time to complete one full cycle of stellar evolution according to standard models. Population 3 stars should still be dominating the landscape. Yet here's a galaxy already in its second or third generation of star formation, already chemically enriched, already bright enough to outshine anything we expected to see. The math doesn't work, the timeline doesn't work. Something in our understanding of cosmic evolution is deeply, fundamentally wrong. Either stars formed far faster than we thought possible, or they started forming much earlier than our models predict, or there's some exotic physics at play that we haven't even conceived of yet. And remember, JWST isn't alone. It's one of dozens of these impossible galaxies that JWST has discovered. Each one pushes the boundaries of what should be possible. Each one demands an explanation that our current theories cannot provide. The cosmic dark ages weren't supposed to be this eventful. They were supposed to be a slow, quiet prelude to the main show. Instead, JWST is revealing that the universe hit the ground running, forming complex structures at speeds that challenge the very foundations of cosmology. So what happens when your observations directly contradict your theories? You have three options. You can question your observations, you can modify your theories, or you can accept that something profound about reality is different than you thought. As we'll see in the next section, astronomers have been forced to confront all three possibilities. The immediate reaction from the astronomical community when JWST's early galaxy discoveries started flooding in was something between excitement and panic. Within the first 6 months of the telescope's operation, over a dozen papers were published with titles that included phrases like crisis in cosmology and tension with the standard model. This wasn't the usual academic caution, this was alarm. Because here's the thing about modern cosmology. It's built on an extraordinarily successful framework called Lambda CDM, or the concordance model. This model describes the universe as being composed of ordinary matter, and dark energy, evolving according to the equations of general relativity from an initial Big Bang. It's been tested and refined over decades through countless observations. It predicted the cosmic microwave background's temperature fluctuations to exquisite precision. It explained the large-scale structure of the universe, the distribution of galaxies across cosmic time, the abundance of light elements. Lambda CDM wasn't just a good theory, it was the best tested theory in all of cosmology. And JWST along with its impossibly early companions, seemed to break it. The problem wasn't subtle. Lambda CDM makes specific predictions about how quickly galaxies can form. It starts with the distribution of dark matter in the early universe, small density fluctuations that act as gravitational seeds. These fluctuations grow over time, pulling in ordinary matter, which eventually collapses to form stars and galaxies. The process has a built-in speed limit determined by the age of the universe, the strength of gravity, and the initial conditions set during the Big Bang. When you run the simulations forward, Lambda CDM tells you that at 290 million years after the Big Bang, you should see mostly small proto-galaxies, perhaps a few tens of millions, of solar masses at most. These should be forming stars at relatively modest rates, maybe a few solar masses per year. They should be chemically primitive, showing little to no enrichment from previous stellar generations. JWST violates every single one of these predictions. Its stellar mass is estimated at several hundred million solar masses. Its star formation rate appears to be tens to hundreds of solar masses per year. Its chemical composition shows clear evidence of multiple generations of enrichment. By every metric that Lambda CDM uses to predict early galaxy properties, this object shouldn't exist. The first response from many astronomers was to question the measurements themselves. Could the redshift be wrong? Redshift measurements, especially at these extreme distances, require careful spectroscopic analysis. Early distance estimates based on photometry alone, where you measure brightness through different filters, can be unreliable. Maybe Jade's GS0 was actually much closer than it appeared, just a weird-looking nearby galaxy that happened to mimic the colors of a distant one. This hope was quickly dashed. JWST's NIR-SPEC instrument provided detailed spectroscopy, measuring the exact wavelengths of emission lines from oxygen and other elements in the galaxy. These measurements are unambiguous. The lines are shifted by a factor of 14.32, corresponding to light that has been traveling for over 13.5 billion years. The redshift is real. The distance is real. The galaxy's extreme age is not in question. So if the observations are solid, maybe the interpretation is wrong. Perhaps what we're seeing isn't starlight at all, but emission from an active galactic nucleus, a supermassive black hole at the galaxy's center accreting matter and pumping out enormous amounts of energy. Black holes can be incredibly luminous, and their light can sometimes mimic stellar emission. If Jade's GSZ140 is powered by a black hole rather than stars, the constraints from Lambda CDM might not apply as strictly. But this explanation creates more problems than it solves. For one, where did the supermassive black hole come from? These objects typically form over hundreds of millions of years through the accumulation and merger of smaller black holes, or through the collapse of massive gas clouds. At 290 million years, there hasn't been enough time for a supermassive black hole to grow through standard channels. You'd need some exotic rapid formation mechanism, which itself violates our models of black hole growth. Moreover, the spectroscopic data doesn't support the black hole hypothesis. The galaxy's light shows strong emission lines characteristic of hot young stars, not the broad emission features typical of active galactic nuclei. The spatial distribution of light is extended, not point-like as you'd expect from a central black hole. Every test astronomers have applied suggests this is genuine starlight from a massive population of young stars. Which brings us back to the uncomfortable conclusion. Lambda CDM, as currently formulated, cannot explain these observations. Something is missing from our models, or something is wrong with our assumptions. The possibilities are both fascinating and disturbing. Maybe dark matter behaves differently in the early universe than we thought, clumping more efficiently and accelerating galaxy formation. Maybe the initial density fluctuations from inflation were larger than our cosmic microwave background measurements suggest, giving gravity a head start. Maybe there's an entirely new physical process we haven't discovered yet, something that speeds up star formation or changes how gas collapses in the early universe. Or maybe, and this is the truly unsettling option, the problem is more fundamental. Maybe our understanding of the Big Bang itself is incomplete. Maybe the universe didn't start from a perfectly smooth, hot, dense state as we assume. Maybe there was structure already present at the very beginning, pre-existing conditions that gave certain regions a massive advantage in forming galaxies. Each of these explanations requires modifications to physics as we understand it. Some require minor tweaks, adjusting parameters within existing theories. Others require entirely new physics, additions to the standard model that we've never observed or predicted. And a few would require us to reconsider the entire framework of Big Bang cosmology, questioning assumptions that have stood for decades. The scientific method demands that we follow the evidence wherever it leads, even when it leads us into uncomfortable territory. Time Chakwatan JD's GSZ140 is evidence that refuses to fit into our comfortable models. It's a data point that insists something about our understanding is wrong. The question is, how wrong? As more galaxies like this continue to emerge from JWST's surveys, the pressure on Lambda CDM is mounting. Astronomers are now racing to find solutions, to modify models, to propose new physics that can accommodate these observations without throwing out everything we've learned. But the clock is ticking. Every new discovery makes the problem more acute. And the most troubling part? Jade's GSZ140 might not even be the worst of it. While Jade's GSZ140 grabbed headlines as the most distant confirmed galaxy, it's part of a larger pattern that's even more perplexing. Astronomers have discovered an entire population of objects in the early universe that don't fit any existing category. They call them little, red dots, and they're rewriting our understanding of what the young cosmos was capable of producing. The name is deceptively simple. These objects appear as small, intensely red points of light in JWST's images, scattered across nearly every deep field observation the telescope has taken. At first glance, they seem insignificant, just faint red smudges among thousands of other galaxies. But when astronomers began analyzing their spectra and measuring their distances, they realized these dots were anything but ordinary. Little red dots exist at redshifts between 5 and 8, corresponding to times when the universe was between 500 million and 1 billion years old. That places them slightly later than Jade's JWST Z14-0, but still firmly in the epoch when galaxies should be small, simple, and struggling to form. Instead, these objects are compact powerhouses, packing enormous amounts of mass and luminosity into incredibly tiny volumes. Here's what makes them so strange. Their red color comes from extreme amounts of dust. Dust in astronomy means tiny particles of carbon, silicon, and other heavy elements created inside stars and blown into space by stellar winds and supernovas. The presence of dust indicates significant chemical enrichment, which in turn requires multiple generations of stars to have lived and died. But at these early times, there shouldn't be enough dust to make galaxies appear this red. The compactness is equally troubling. Many little red dots have effective radii of just a few hundred light years, making them smaller than most globular clusters in our own galaxy. Yet they're emitting light equivalent to billions of solar masses worth of stars, or alternatively, emission from actively feeding supermassive black holes. The energy density in these objects is staggering, far higher than anything we see in the local universe. When spectroscopy revealed their nature, the mystery deepened. Some little red dots show clear signatures of star formation, with emission lines from ionized hydrogen and oxygen indicating massive bursts of stellar birth. Others display broad emission lines characteristic of supermassive black holes accreting matter at prodigious rates. And disturbingly, many show both signatures simultaneously, suggesting they're forming stars and growing black holes at the same time in the same compact region. This dual nature is something we don't fully understand. In the modern universe, star formation and black hole accretion tend to be mutually exclusive. When a supermassive black hole feeds actively, it generates powerful winds and radiation that blow away nearby gas, shutting down star formation. Conversely, when galaxies undergo intense starbursts, they consume their gas supply quickly, leaving little for a central black hole to accrete. Yet little red dots seem to be doing both simultaneously in regions so small that the competing processes should interfere with each other catastrophically. The black holes themselves present another problem. Several little red dots contain supermassive black holes with masses exceeding 100 million solar masses. At less than 1 billion years after the Big Bang, these black holes are far too massive to have grown through standard accretion. Black holes grow by consuming matter, but there's a physical limit to how fast they can feed called the Eddington limit. Above this limit, the radiation pressure from the infalling matter becomes so intense that it pushes away additional material, choking off further growth. If you start with a stellar mass black hole, say 30 solar masses from the collapse of a massive star, and let it accrete at the Eddington limit continuously from the Big Bang onward, you still can't reach 100 million solar masses by 1 billion years. The math simply doesn't work. To grow this large this quickly, black holes would need to exceed the Eddington limit by factors of 10 or more, something that should be physically impossible under standard physics. This has led to radical proposals. Maybe the first black holes didn't form from stars at all, but from the direct collapse of massive gas clouds in the early universe, creating seed black holes that were already thousands or even millions of solar masses at birth. These direct collapse black holes could bypass the slow stellar formation pathway, giving them a head start on growth. But direct collapse requires very specific conditions: pristine gas clouds with no metal contamination, intense radiation fields to keep the gas from fragmenting into stars. These conditions should be rare, yet little red dots are numerous, appearing in nearly every JWST deep field. Another possibility is super Eddington accretion, where black holes somehow overcome the radiation pressure barrier and consume matter at rates far beyond what theory predicts should be possible. Some models suggest that if the accretion flow is sufficiently thick and optically opaque, radiation might be trapped long enough to allow higher feeding rates. But these models are speculative, and observational evidence for sustained super Eddington accretion is limited. The abundance of little red dots is itself a puzzle. Before JWST, we expected supermassive black holes in the early universe to be exceedingly rare. The black hole at the center of the Milky Way took billions of years to grow, to just 4 million solar masses, finding dozens of black holes 10 times larger at a tenth. The age suggests that black hole formation and growth were vastly more efficient in the early universe than we ever imagined. But perhaps the most unsettling aspect of little red dots is what they imply about cosmic structure formation. If these compact, massive objects were common a billion years after the Big Bang, they must have formed from exceptionally dense regions in the early universe. This requires stronger initial density fluctuations than we infer from the cosmic microwave background, or some mechanism that amplified those fluctuations more efficiently than our models predict. Some astronomers have proposed that little red dots represent a transitional phase in galaxy evolution, a brief period when galaxies are compact, dusty, and rapidly building both their stellar populations and central black holes before expanding into the more familiar structures we see later. But this raises questions about what triggers this phase and why it appears to be so common. Others suggest we're witnessing the formation of the seeds that will eventually become the supermassive black holes in present-day giant galaxies. If true, it means black hole growth was front-loaded in cosmic history, with most of the mass accumulation happening very early. This contradicts hierarchical models that predict steady growth over billions of years through mergers and gradual accretion. The little red dots have become emblematic of JWST's impact on cosmology. They represent a class of objects we didn't predict, exhibiting properties we struggle to explain, existing in numbers we can't account for with existing theories. Every new observation adds detail to the picture, but that detail only makes the puzzle more complex. And here's the kicker, we've only begun to scratch the surface. JWST has surveyed a tiny fraction of the sky. The little red dots we've found so far might just be the brightest, most extreme examples of a much larger population waiting to be discovered. As JWST continues its mission, as it peers deeper and samples more of the early universe, we're likely to find even stranger objects that push our theories even further. The little red dots are teaching us that the early universe was a far more violent, active, and complex place than we ever imagined. They're forcing us to reconsider everything from how stars form to how black holes grow to how galaxies assemble. And they're doing it all while shining at us from an era we thought we understood. We didn't. Just underestimate the early universe. We fundamentally misread it. If little red dots represent one crisis for cosmology, the discovery of unexpectedly massive galaxies at high redshift represents another, arguably more fundamental challenge. JWST hasn't just found galaxies that are bright or compact or chemically enriched too early. It's found galaxies that are simply too massive to exist at all. Mass is the fundamental currency of cosmology. Everything in our models depends on how quickly matter can accumulate into structures. Dark matter halos grow through gravitational collapse, pulling in baryonic matter that eventually forms stars and galaxies. This process has a speed limit set by the age of the universe and the efficiency with which gas can cool, collapse, and convert into stars. Lambda CDM makes precise predictions about the maximum mass a galaxy can achieve at any given cosmic time. In early 2023, several teams analyzing JWST data published bombshell findings. They had identified galaxies at redshifts between 7 and 10, corresponding to 500 to 700 million years after the Big Bang, with estimated stellar masses exceeding 10 billion solar masses. For context, our Milky Way has a stellar mass of roughly 60 billion solar masses, accumulated over 13 billion years. These early galaxies appear to have built up a significant fraction of the Milky Way's total stellar content in less than 5% of the time. The number seemed impossible. To build 10 billion solar masses of stars in just 500 million years requires converting gas into stars at rates far exceeding anything we observe in even the most extreme starburst galaxies today. You'd need star formation rates of 20 to 50 solar masses per year sustained continuously from the Big Bang onward with essentially perfect efficiency. No cooling time, no feedback from supernovas disrupting the process, no periods of quiescence. Just relentless, uninterrupted star formation at maximum possible rates. Even that wouldn't be enough if you're starting from the initial conditions we observe in the cosmic microwave background. The density fluctuations at recombination were tiny, just 1 part in 100,000. These fluctuations had to grow through gravitational instability, but growth takes time. Dark matter halos need to collapse and virialize, forming potential wells deep enough to trap gas. The gas needs to cool and settle into those wells before it can form stars. Every step in this process has a characteristic timescale, and when you add them up, you simply can't build 10 billion solar mass galaxies by 500 million years. The initial reaction was skepticism, mass estimates. For distant galaxies are notoriously uncertain. You measure the brightness of a galaxy in different wavelength bands, then fit those measurements to models of stellar populations to infer the total stellar mass. But these models depend on assumptions about the star formation history, the initial mass function of stars, the amount of dust obscuration, and other factors that can vary widely. Small changes in these assumptions can lead to large changes in estimated mass. Perhaps the early JWST observations were being misinterpreted. Maybe these galaxies weren't as massive as they appeared. Maybe they were dustier than expected, or maybe they contained unusual stellar populations that made them appear more massive in the models. Several teams went back to reanalyze the data with more sophisticated techniques, accounting for uncertainties and potential systematic errors. The result? The mass estimates came down, but not by much. Even with conservative assumptions and careful accounting of uncertainties, many of these early galaxies still appear to have stellar masses of several billion solar masses. Still too massive, still too early, still in fundamental tension with Lambda CDM predictions. This is where the phrase crisis in cosmology started appearing in academic papers. A crisis in science occurs when observations systematically contradict well-established theory in ways that can't be easily explained by measurement errors or misinterpretations. The massive early galaxies represented exactly this kind of crisis. They weren't outliers or flukes. They were showing up repeatedly across multiple JWST surveys, observed by different teams using different analysis methods, all arriving at the same troubling conclusion. Some astronomers proposed that the solution might lie in pushing star formation to even earlier times. If the first stars began forming at 100 or 150 million years after the Big Bang, rather than the 200 to 300 million years predicted by standard models, you'd have more time to build up stellar mass. But this just pushes the problem back. You still need to explain how stars could form that early, when the universe should still be too smooth and homogeneous to allow significant structure formation. Others suggested that star formation efficiency was much higher in the early universe. Modern galaxies convert only about 10 to 30% of their available gas into stars over their lifetimes, with the rest being ejected by supernovas and stellar winds or simply never collapsing. Maybe early galaxies were more efficient, converting 50 or even 70% of their gas into stars. This would reduce the time needed to build up mass, but it requires explaining why early star formation was so much more efficient than what we observe today. A more radical proposal involves modifying the initial conditions of the universe itself. What if the cosmic microwave background doesn't tell us the whole story? What if there were additional density fluctuations on small scales that didn't leave an imprint in the microwave background but did seed early structure formation? These fluctuations could come from exotic physics during inflation, the rapid expansion phase that occurred in the first fraction of a second after the Big Bang. But invoking new physics during inflation is a desperate measure akin to adding epicycles to save a failing theory. The most troubling possibility is that our understanding of dark matter is incomplete. Lambda CDM assumes dark matter is cold, meaning it moves slowly compared to the speed of light and clumps efficiently under gravity. This cold dark matter forms the scaffolding on which galaxies build. But what if dark matter has additional properties we haven't accounted for? What if it can interact with itself in ways that enhance structure formation? What if there are multiple types of dark matter with different behaviors? These questions might sound academic, but they strike at the heart of cosmology. Dark matter makes up 85% of the matter in the universe. We've built an entire cosmological model around its properties, inferred from gravitational effects and large-scale structure observations. If our picture of dark matter is wrong, even slightly, the implications ripple through every aspect of our understanding of cosmic evolution. The massive galaxy problem has galvanized the theoretical community. Dozens of papers have been published proposing modifications to Lambda CDM, new feedback mechanisms, alternative dark matter models, and exotic physics during the early universe. Each proposal attempts to reconcile the observations with theory, to find a way to make the impossible galaxies possible without breaking everything else that Lambda CDM gets right. But here's the uncomfortable truth. We might not find a solution that preserves the elegant simplicity of the concordance model. We might be forced to accept that the universe is more complicated, more baroque, with additional physics and processes that we've neglected because they weren't necessary to explain previous observations. JWST is showing us a universe that doesn't play by the rules we thought we'd figured out. The massive early galaxies aren't just an anomaly, they're a wake-up call. They're telling us that somewhere in our chain of reasoning, from the Big Bang to the present day, we've made assumptions that don't hold. And until we identify which assumptions are wrong and how to fix them, we're left staring at data that shouldn't exist, trying to understand a universe that refuses to make sense. The crisis isn't going away. If anything, it's getting worse. Beyond mass and brightness, there's another dimension to the early galaxy problem that's equally disturbing: structural maturity. JADE's GS Z14-0. And its contemporaries don't just exist too early and grow too fast. Many of them look far too organized, too evolved, too much like modern galaxies when they should still be chaotic, irregular lumps of stars struggling to find their shape. Galaxy morphology, the study of galaxy shapes and structures, has long been a cornerstone of understanding cosmic evolution. In the local universe, we observe a clear dichotomy. There are spiral galaxies like the Milky Way with ordered rotating disks, spiral arms, and central bulges. And there are elliptical galaxies, smooth, featureless spheroids dominated by random stellar orbits rather than organized rotation. Between these extremes lie irregular galaxies, chaotic systems without clear structure, often the result of ongoing mergers or intense star formation that hasn't yet settled into equilibrium. The traditional picture of galaxy evolution held that early galaxies should be predominantly irregular. Structure takes time to develop. A rotating disk requires gas to settle into a plane through countless collisions, radiating away energy until it finds its minimum energy configuration. Spiral arms emerge from density waves in already established disks. Bulges grow through the accumulation of stars scattered by gravitational interactions. None of these processes happen quickly. They require hundreds of millions, even billions of years to produce the ordered structures we see in mature galaxies today. Yet when JWST began resolving the detailed structures of galaxies at redshifts above 6, astronomers found something unexpected. Many of these early galaxies already show signs of structural maturity: rotating disks, central concentrations, in some cases, even hints of spiral structure, features that shouldn't exist yet according to the timescales predicted by galaxy formation theory. One particularly striking example is a galaxy at redshift 7.3, existing just 700 million years after the Big Bang. Spectroscopic observations reveal it has a clear velocity gradient, with one side moving toward us and the other side moving away, exactly what you'd expect from a rotating disk. The rotation velocity is high, around 150 kilometers per second, indicating a substantial mass. But more importantly, the rotation appears ordered and stable, not the chaotic motions you'd expect from a system still in the process of assembly. The existence of such a disk this early poses a serious challenge. Disk formation requires specific conditions. You need a relatively smooth inflow of gas that can settle into a rotating configuration without being disrupted by mergers or violent feedback. You need enough time for the gas to lose its random motions through collisions and interactions, allowing it to collapse into a thin plane. Most models predict this process takes at least 1 billion years, often longer. Yet here's a galaxy showing clear disk rotation at less than half that age. Another galaxy at redshift 8.5, observed at just 600 million years after the Big Bang, displays what appears to be a two-component structure: a central bulge surrounded by a more extended envelope. This morphology is typical of lenticular or early-type spiral galaxies in the modern universe, systems that have undergone significant dynamical evolution. The presence of such structure this early suggests that even in the first 500 million years of cosmic history, Some galaxies had already experienced complex formation histories involving multiple episodes of star formation, possible mergers, and dynamical settling. The paradox deepens when you consider what these structures imply about the underlying dark matter halos. Disk galaxies require relatively undisturbed dark matter halos that are roughly spherical or mildly triaxial. If a halo experiences major mergers, the disk gets destroyed, heated up into a spheroid through violent relaxation. The fact that we're seeing stable disks at these early times means their host halos must have been remarkably quiescent, avoiding major mergers for hundreds of millions of years. But Lambda CDM predicts exactly the opposite. In the early universe, the merger rate should be high. Small halos are constantly colliding and combining, building up larger structures through hierarchical assembly. This environment is hostile to disk formation. Every merger disrupts whatever ordered structure might be developing, forcing the system to start over. Disks should be rare at high redshift, only becoming common later in cosmic history once the merger rate declines and galaxies have time to settle into equilibrium. The observations suggest otherwise. Disks appear to be surprisingly common even at redshifts of 6 to 8. This either means the merger rate was lower than predicted, or galaxies can form and maintain disks even in violent environments, or our understanding of how mergers affect galaxy structure is incomplete. Some researchers have proposed that early disks might form through rapid, smooth gas accretion along cosmic filaments. If gas flows into a galaxy along narrow streams rather than through random directions, it can naturally acquire angular momentum and settle into a rotating configuration. This cold mode accretion could potentially form disks faster than traditional models predict. But even cold mode accretion requires time for the gas to cool and organize, and it's unclear whether it can operate efficiently enough in the first few 100 million years of cosmic history. Another puzzle relates to the sizes of these early galaxies. Many are surprisingly compact, with half their light coming from regions just a few hundred light years across. This is much smaller than typical galaxies of similar mass today. Our Milky Way's stellar disk extends for 50,000 light years. Why were early galaxies so much denser? The answer likely involves gas content and dynamics. Early galaxies probably had much higher gas fractions than modern galaxies, with gas making up 50% or more of their total baryonic mass compared to just 10 to 20% in galaxies today. This gas-rich nature, combined with the higher density of the early universe, would naturally lead to more compact structures. But it also raises questions about how these compact systems eventually expanded into the more extended galaxies we see later. The morphological maturity we're observing also has implications for the star formation histories of these galaxies. Structured galaxies with ordered rotation tend to have more stable, sustained star formation compared to irregular galaxies where star formation is bursty and chaotic. If early galaxies were already settling into stable configurations, it suggests their star formation might have been more continuous and efficient than models predict, potentially explaining how they built up such large stellar masses so quickly. But there's a darker interpretation. What if the maturity we're seeing isn't real, but an illusion created by observational biases? JWST, for all its power, has limited angular resolution. A galaxy at redshift 8 that appears smooth and regular might actually be composed of multiple, smaller clumps that we simply can't resolve. What looks like a rotating disk might actually be several proto-galactic fragments orbiting each other. We could be mistaking complexity on small scales for simplicity on large scales. This is a legitimate concern, and it's led some astronomers to caution against over-interpreting early morphological observations. We need higher resolution imaging, perhaps from future extremely large telescopes on the ground, or from next-generation space telescopes, to truly understand what these early galaxies look like in detail. Yet even accounting for resolution limits, the evidence for structural maturity remains compelling. The kinematic data showing ordered rotation doesn't depend on resolving fine details. The presence of velocity gradients and rotation curves can be measured spectroscopically even when we can't see individual star-forming regions. And those data consistently point toward galaxies that have achieved a level of dynamical organization unexpected for their age. The maturity paradox forces us to confront an uncomfortable question. How much do we really understand about galaxy formation? We've built sophisticated simulations that can reproduce many features of the galaxy population we observe today. But those simulations were calibrated on observations of relatively nearby galaxies, systems we can study in exquisite detail. We've been extrapolating those models backward in time, assuming the same physical processes operate in the early universe. JWST is showing us that extrapolation was naive. The early universe wasn't just a younger, smaller version of today. It was a fundamentally different environment with different conditions, different processes, perhaps even different dominant physics. Galaxies didn't grow up slowly through adolescence into mature adulthood. They seem to have been born nearly fully formed, achieving in hundreds of millions of years what we thought took billions. This isn't just surprising, it's paradigm shifting, and as we'll see, it's connected to even deeper mysteries about the nature of cosmic time itself. One of the most perplexing aspects of JWST and other early galaxies isn't just that they exist, but what they're made of. When astronomers analyze the spectrum of light from these ancient objects, they're seeing chemical fingerprints that tell a story of cosmic evolution happening at impossible speeds. Every element heavier than hydrogen and helium in the universe was forged inside stars. Carbon, nitrogen, oxygen, silicon, iron, all of these elements are created through nuclear fusion in stellar cores and dispersed into space when stars die, either through gentle stellar winds or violent supernova explosions. This process of chemical enrichment is gradual, building up over multiple generations of stars. Each generation is born from gas clouds slightly richer in heavy elements than the last, creating a chemical timeline that traces cosmic history. In the modern universe, we can read this timeline clearly. The oldest stars in the Milky Way's halo, born over 13 billion years ago, contain almost no heavy elements. They're composed of roughly 75% hydrogen and 25% helium, nearly identical to the primordial composition that emerged from the Big Bang. These population 2 stars represent early stellar generations formed before significant chemical enrichment had occurred. Our Sun, by contrast, is a relatively young star, just 4.6 billion years old. Its atmosphere contains about 2% heavy elements by mass, accumulated from billions of years of previous stellar generations enriching the interstellar medium. This progressive enrichment over cosmic time is one of the pillars of stellar evolution theory. It's predictable, well understood, and observationally confirmed across countless stars in our galaxy and beyond. JWST breaks this timeline. Spectroscopic observations reveal the presence of oxygen at levels that suggest significant prior enrichment. Oxygen is created primarily in massive stars with lifetimes of just a few million years. These stars must form, live, and die as supernovas to release their oxygen into the surrounding gas. Then new stars must form from that enriched material. This cycle needs to repeat multiple times to reach the oxygen abundances observed in JWST. But here's the problem. At 290 million years after the Big Bang, there simply hasn't been enough time for multiple cycles of stellar birth and death. Even if the very first stars formed at 100 million years, which is earlier than most models predict, you'd only have 190 million years for stellar evolution. Massive stars that produce oxygen live for 3 to 10 million years. After they explode, the enriched gas needs time to cool and collapse into new stars. This process might take another 10 to 50 million years depending on conditions. If you're generous with the timescales and assume everything happens at maximum speed, you might squeeze in 3 or 4 generations of stars by 290 million years. But the oxygen abundances in JWST suggest more enrichment than 3 or 4 generations could provide, even under ideal circumstances. It's as if cosmic chemical evolution was running on fast forward, achieving in a fraction of a billion years what should take several billion. The nitrogen detection makes things even stranger. Nitrogen has a more complex origin than oxygen. While oxygen comes primarily from massive stars that explode as core collapse supernovas, nitrogen is thought to be produced mainly in intermediate mass stars through the CNO cycle, a set of nuclear reactions that converts carbon and oxygen into nitrogen. These intermediate mass stars live much longer than their massive counterparts, typically 100 million to a billion years depending on their mass. The presence of significant nitrogen in such an early galaxy suggests that not only have massive stars already lived and died, but intermediate mass stars have also completed their life cycles and released their products into the interstellar medium. This pushes the formation of the first stars back even earlier, possibly to 50 or 100 million years after the Big Bang, a time when the universe should still be far too smooth and uniform to allow star formation. Some researchers have proposed alternative explanations. Maybe the first stars, population 3 stars, were different from any stars we see today. Theory suggests these pristine stars, formed from gas containing no heavy elements, could have been extraordinarily massive, perhaps 100 to 300 solar masses. Such hypermassive stars would burn incredibly hot and die in spectacular explosions called pair instability supernovas, which could produce unusually high yields of certain elements. If population 3 stars systematically produced more oxygen and nitrogen per supernova than modern stars do, it might explain the rapid enrichment we're seeing. But this solution requires that essentially all the first stars were hypermassive, which seems unlikely. Computer simulations of star formation in primordial gas suggest a range of masses should form, not just giants. And even if the first stars were all massive, there's still the timing problem. You need those stars to form, evolve, and explode, then new stars to form from the debris, all within that narrow window of time. Another possibility involves top-heavy initial mass functions. The initial mass function describes the distribution of stellar masses when stars form. In the local universe, for every massive star that forms, hundreds of low-mass stars are born. But maybe in the early universe, the mass function was skewed toward high-mass stars. If gas clouds preferentially fragmented into massive stars rather than a mix of masses, you'd produce more supernovas per unit of star formation, accelerating chemical enrichment. This idea has some theoretical support. The conditions in the early universe were very different from today. Gas was hotter, denser, and metal-free, all factors that might favor the formation of massive stars over low-mass ones. But we don't have direct observational evidence for this top-heavy mass function, and some simulations suggest that even pristine gas should produce a broad range of stellar masses. There's also the dust problem. Dust and heavy elements are intimately connected. Dust grains are composed of elements like carbon, silicon, oxygen, and iron condensed into solid particles. The amount of dust in a galaxy is a direct tracer of its chemical enrichment. JWST observations of some early galaxies show surprising amounts of dust, far more than should exist given their age. Dust formation itself takes time. After a supernova explosion, the ejected material needs to cool and condense into solid grains, a process that can take thousands to millions of years depending on density and temperature. Time the worsens. The presence of substantial dust in galaxies just a few 100 million years old suggests either very efficient dust formation or an earlier start to stellar evolution than we've assumed. One of the most radical proposals to explain rapid chemical enrichment involves supermassive stars. Not the 100 to 300 solar mass population 3 stars, but hypothetical monsters of 10,000 to 100,000 solar masses that could have formed in the densest regions of the early universe. These supermassive stars would have lifetimes of just a few million years and would enrich their surroundings massively when they died. A single supermassive star could produce as much chemical enrichment as thousands of normal massive stars. The problem is, we have no direct evidence these supermassive stars ever existed. The conditions required to form them are extreme and may not have been common in the early universe. And even if they did form, they'd need to be distributed widely enough to enrich the volume of space that eventually became galaxies like JWST Z14-0. This requires fine-tuning that seems unlikely without some physical mechanism to ensure it happens. The chemical enrichment mystery extends beyond individual galaxies. When you survey many early galaxies, you find a wide range of chemical compositions. Some show surprisingly high enrichment, like JWST Z14-0, while others appear more pristine, closer to what we'd expect for their age. This diversity is itself puzzling. If chemical enrichment proceeds through well-understood stellar processes, we'd expect a relatively narrow range of compositions at any given cosmic time, determined by the average star formation history. The observed scatter suggests that galaxy evolution in the early universe was highly stochastic. with different regions experiencing wildly different rates of star formation and enrichment. But this contradicts the relatively smooth initial conditions we infer from the cosmic microwave background. How do you get such large variations in evolution from such uniform starting conditions? One possibility is that feedback processes were more important in the early universe than we've appreciated. When massive stars explode as supernovas, they don't just enrich the surrounding gas with heavy elements, they also heat it and blow it away, potentially suppressing further star formation. If some protogalaxies experienced strong feedback that shut down their star formation early, while others avoided this fate, you could generate a wide range of enrichment levels. But modeling these feedback processes is notoriously difficult. They involve complex physics spanning many orders of magnitude in scale, from individual supernovas affecting regions a few light years across to galactic winds extending for hundreds of thousands of light years. Our simulations are only beginning to capture this complexity with adequate resolution. The chemical composition of early galaxies also has implications for the first generation of planets. Heavy elements are essential for forming rocky planets like Earth. If galaxies were already significantly enriched by 290 million years after the Big Bang, it means potentially habitable planets could have formed far earlier than we previously thought. This pushes back the possible origin of life in the universe by billions of years, a profoundly unsettling thought. Chemical enrichment is supposed to be one of the reliable clocks of cosmic evolution. The buildup of heavy elements over time provides an independent measure of a galaxy's age and history. But JWST 14.0 and its companions are showing us that this clock was running fast in the early universe, ticking forward, at a rate we can't yet explain. And when your clocks don't agree with your calendar, you have to question whether you're measuring time correctly at all. If chemical enrichment is happening too fast, star formation itself appears to be operating at rates that defy explanation. JWST 14.0 and similar galaxies aren't just forming stars, they're forming them at blistering speeds that push the boundaries of what physics should allow. Star formation rate is measured in solar masses per year, essentially how many sun-sized stars worth of gas a galaxy converts into stars annually. In the local universe, this rate varies enormously. Quiescent galaxies like ellipticals might form less than 1 solar mass of stars per year, while the most extreme starburst galaxies can reach rates of several hundred solar masses per year. The Milky Way, a typical spiral galaxy, forms about 2 solar masses of stars annually. These rates are limited by fundamental physics. Stars form when giant molecular clouds collapse under their own gravity. But several processes resist this collapse. Gas pressure pushes outward, opposing gravity. Magnetic fields thread through the clouds, providing additional support. Turbulence stirs the gas, preventing smooth collapse. And once stars begin forming, they fight back against their own creation through feedback processes. Young massive stars emit intense ultraviolet radiation that heats surrounding gas, increasing its pressure and making further collapse more difficult. Stellar winds blow material away from star-forming regions. And when the most massive stars die as supernovas, the explosions can completely disrupt nearby molecular clouds, shutting down star formation for millions of years while the gas disperses and cools. These feedback mechanisms create a natural regulation of star formation. Galaxies can't simply convert all their gas into stars instantaneously. The process is self-limiting, with each generation of stars making it harder for the next generation to form. This is why even the most extreme starburst galaxies in the local universe have star formation efficiencies of only 10 to 30% over their lifetimes. Most of the gas either remains unconverted or gets ejected before it can form stars. JWST 14.0 appears to be violating these limits. Estimates suggest star formation rates of 50 to potentially over 100 solar masses per year, sustained in a galaxy that's only 1,600 light-years across. For comparison, that's like cramming the entire star-forming activity of 50 Milky Ways into a region smaller than the distance between Earth and the nearest large star cluster. The energy density in such an environment would be staggering. With that many massive stars forming in such a small volume, the ultraviolet radiation field would be millions of times more intense than anything we observe in nearby galaxies. This radiation should heat the surrounding gas to temperatures where it can't collapse to form more stars. It should create enormous pressure that drives powerful galactic winds, expelling gas from the galaxy faster than new gas can flow in. Yet somehow JWST 14.0 is maintaining this extreme star formation. Either the feedback processes we understand from local galaxies don't work the same way in the early universe, or there's some mechanism keeping fresh gas flowing into the star-forming regions fast enough to overcome the feedback. One possibility is that early galaxies had access to vastly more gas than modern galaxies. In the early universe, galaxies were embedded in denser cosmic environments with more material available for accretion. If gas was streaming into JWST 14.0 along cosmic filaments at high rate, it might replenish the star-forming reservoir faster than feedback could deplete it. But this explanation has limits. Even with abundant gas, you still face the cooling problem. Gas needs to shed energy and cool down before it can collapse into stars. In the modern universe, this cooling is facilitated by trace amounts of heavy elements that radiate energy efficiently. But early galaxies had fewer heavy elements, making cooling less efficient. This should slow star formation, not accelerate it. Some researchers have proposed that the intense radiation fields in early galaxies might actually help, rather than hinder star formation through a process called radiative feedback. If the radiation is strong enough, it can compress gas clouds from the outside, triggering collapse that might not otherwise occur. This is similar to how massive stars can trigger secondary star formation in their surroundings before their feedback becomes destructive. Another factor might be the absence of heavy elements. While metals help gas cool, they also provide opacity that can trap radiation inside star-forming clouds. In metal-poor gas, radiation escapes more easily, potentially reducing some feedback effects. The gas might fragment more readily into stars because it's less able to support itself against gravity once collapse begins. There's also the possibility that the star formation we're observing isn't sustained, but represents a brief, intense burst. Perhaps JWST 14.0 is caught in a special moment of its evolution, undergoing a temporary explosion of star formation that will burn out quickly. If we're seeing these galaxies during their peak activity, we might be overestimating their typical star formation rates. But this statistical argument faces a problem. JWST is finding many galaxies with similarly high star formation rates at early times. If each one represents a brief burst, we're incredibly unlucky to catch so many of them in that fleeting phase. The number suggests that extreme star formation might be normal rather than exceptional in the early universe. The star formation rate problem connects directly to the mass problem discussed earlier. If you want to build a galaxy with several hundred million solar masses and stars by 290 million years after the Big Bang, you need sustained high star formation rates throughout that entire period. You can't afford significant downtime or periods of quiescence. This requires maintaining conditions favorable for star formation continuously for hundreds of millions of years, resisting all the feedback processes that should shut it down. Some models invoke continuous cold gas accretion to maintain these high rates. In this scenario, gas flows smoothly onto the galaxy along cosmic filaments, never getting shock heated to high temperatures. This cold gas can cool and form stars efficiently, potentially sustaining high star formation rates indefinitely as long as the gas supply lasts. But simulations struggle to reproduce this. When you model galaxy formation in the early universe with realistic physics, feedback tends to be violent and disruptive. Supernovas create hot bubbles that merge into galactic-scale winds. These winds can eject significant fractions of a galaxy's gas reservoir, temporarily or permanently shutting down star formation. Getting sustained high star formation rates in simulations requires either weakening feedback artificially or finding special circumstances that are rare in the simulation volume. There's another wrinkle. The initial mass function might be different in the early universe. If early star formation preferentially produced massive stars over low-mass ones, each generation of star formation would produce more feedback because massive stars are the ones that explode as supernovas. This would make sustained star formation even harder, not easier. Alternatively, if the early initial mass function was actually bottom-heavy, producing more low-mass stars than today, you'd need even higher total star formation rates to produce the luminosity we observe. Low-mass stars are faint, so you'd need many more of them to generate the same amount of light. This makes the star formation rate problem worse, not better. The spatial distribution of star formation adds another layer of complexity. In local galaxies, star formation is often patchy, concentrated in molecular clouds scattered throughout the disk. But in compact early galaxies like JWST Z14-0, star formation must be happening in a much smaller volume. This concentration should enhance feedback effects because supernovas occurring in proximity can combine their energy, creating more powerful collective winds. Yet somehow these compact starbursts persist. Either the feedback is less effective than we think, or the gas supply is more resilient than our models predict, or there's some physical process we haven't identified that stabilizes star formation in these extreme environments. One speculative idea involves magnetic fields. Strong magnetic fields can channel gas flows and potentially shield star-forming regions from some feedback effects. If early galaxies had unusually strong or structured magnetic fields, they might create protected zones where star formation could proceed despite the intense radiation and winds from nearby regions. But we have little observational constraint on magnetic field strengths in galaxies at these redshifts. The star formation rate problem also raises questions about the longevity of these galaxies. If JWST 0 is forming stars at 100 solar masses per year, and it only contains a few 100 million solar masses of stars, that means it built its entire stellar population in just a few million years of active star formation. What happened before and after? Was there an earlier phase we're not seeing? Will star formation continue, or is the galaxy about to shut down? The duty cycle of star formation, what fraction of time a galaxy spends actively forming stars versus lying quiescent, becomes crucial. If early galaxies form stars in brief, intense bursts with long, quiescent periods in between, we need to understand what triggers these bursts and what shuts them down. If star formation is continuous, we need to explain how feedback is suppressed. Some astronomers have suggested that the extreme star formation rates might indicate we're witnessing galaxy mergers. When two gas-rich galaxies collide, the interaction can compress gas and trigger intense starbursts that far exceed the normal star formation rates of the individual galaxies. If many of the bright early galaxies we're seeing are actually merger-triggered starbursts, it might explain their extreme properties. But this explanation requires that mergers were extraordinarily common in the early universe, happening frequently enough that we catch many galaxies in this phase. And it requires that even the smallest protogalaxies could trigger massive starbursts when they merged, something not obviously supported by merger simulations. The star formation rate problem isn't just about numbers, it's about understanding the physical processes that govern how gas turns into stars under conditions very different from what we observe locally. Every aspect of the problem, the gas supply, the cooling mechanisms, the feedback processes, the role of magnetic fields and turbulence, operates in regimes we've never directly observed and can barely simulate. JWST Z14-0 is showing us that star formation in the early universe was not simply a scaled-down version of what we see today. It was fundamentally different, operating under different rules or with different efficiency. And until we understand what allowed these galaxies to form stars so rapidly, we can't claim to understand galaxy formation at all. The problems we've discussed so far, mass, maturity, chemical enrichment, star formation rates, all trace back to a single underlying framework, Lambda CDM cosmology, and its predictions about how dark matter structures the universe. If early galaxies are violating our expectations this dramatically, perhaps the issue lies with dark matter itself. Dark matter constitutes 85% of all matter in the universe, yet we've never directly detected a single dark matter particle. Everything we know about it comes from its gravitational effects, how it holds galaxies together, how it bends light, how it seeds the formation of cosmic structure. We've built an entire cosmological model around the assumption that dark matter is cold, moving slowly, interacting only through gravity, clumping efficiently under its own gravitational pull. But what if dark matter behaves differently in the early universe than it does today? Temperature, density, and the expansion rate were all vastly different in the first few 100 million years after the Big Bang. Under these extreme conditions, dark matter might exhibit properties we've never observed in the modern cosmos. One possibility is that dark matter can interact with itself through forces beyond gravity. Self-interacting dark matter could scatter off itself, redistributing energy and momentum in ways that affect how quickly structures form. If these self-interactions were stronger in the early universe due to higher densities, they might have accelerated the collapse of dark matter halos, giving galaxy formation a head start. Another option involves dark matter being not one particle but several. Multiple species of dark matter with different properties could coexist, with each playing different roles in structure formation. Perhaps one component is truly cold and forms the large-scale scaffolding, while another is slightly warmer and affects small-scale structure. The interplay between these components might create conditions favorable for rapid early galaxy formation. There's also the question of primordial black holes. If a fraction of dark matter consists of black holes formed in the first seconds after the Big Bang, they could seed galaxy formation in ways regular particle dark matter cannot. These primordial black holes would act as gravitational anchors, pulling in gas more efficiently than diffuse dark matter halos, and potentially explaining the early appearance of massive structures. The initial power spectrum, how density fluctuations varied with scale immediately after the Big Bang, might also differ from what we infer from the cosmic microwave background. If there were enhanced fluctuations on small scales that the CMB doesn't reveal, dark matter could have started clumping earlier and faster, providing more time for galaxies to form by the era JWST is observing. Each of these possibilities requires modifications to the standard dark matter picture. They're not wild speculation. They're serious theoretical proposals backed by mathematical models and sometimes even experimental searches. But they all share a common feature. They make dark matter more complex, adding parameters and possibilities that we haven't needed to explain observations of the local universe. The challenge is that dark matter modifications can't just fix the early galaxy problem. They must also preserve all the successes of Lambda CDM in explaining the cosmic microwave background, the large-scale distribution of galaxies, gravitational lensing observations, and dozens of other phenomena. Any change to dark matter physics ripples through the entire cosmological model, potentially breaking things that already work. Some researchers argue that rather than modifying dark matter, we should reconsider how ordinary matter behaves in the early universe. Perhaps gas cooling was more efficient than we think, or feedback was weaker, or some combination of factors allowed galaxies to form from standard dark matter halos much faster than our current models predict. This approach keeps the dark matter simple but requires rethinking the complex astrophysics of star and galaxy formation. The truth might involve both. Dark matter could have subtle properties we haven't discovered, and galaxy formation physics could operate differently under early universe conditions. Disentangling these effects requires observations that can constrain both dark matter properties and astrophysical processes independently. JWST is providing some of these constraints. By measuring how galaxies cluster in space at different redshifts, we can infer properties of the underlying dark matter distribution. By studying the smallest galaxies, we probe the minimum mass of dark matter halos that can form stars. Each observation chips away at the parameter space, narrowing the range of possible dark matter models. But we're still left with uncomfortable questions. If dark matter has properties we haven't discovered after decades of searching, what else might we be missing? And if standard cold dark matter is correct, why does galaxy formation in the early universe seem to defy all our predictions? The answer will determine whether JWST 4.0 represents a crisis for cosmology or merely a gap in our understanding of astrophysics. Either way, dark matter holds the key. Cosmologists don't just theorize about galaxy formation, they simulate it. Massive computer models run the equations of gravity, gas dynamics, star formation, and feedback, evolving virtual universes from the Big Bang to the present day. These simulations have been remarkably successful at reproducing the galaxy population we observe in the local universe. But they're failing spectacularly when it comes to the early universe JWST is revealing. The most sophisticated simulations track billions of particles representing dark matter and gas, following their evolution over cosmic time. They include recipes for when gas cools enough to form stars, how supernovas inject energy back into their surroundings, how black holes grow and affect their host galaxies. These aren't arbitrary rules. They're based on physics calibrated against observations of nearby galaxies. When you run these simulations forward to redshift 14, they predict that galaxies should be small, dim and rare. The largest halos might contain a few tens of millions of solar masses in stars. Typical star formation rates should be a few solar masses per year at most. Chemical enrichment should be minimal, with metallicities a tiny fraction of solar values. JWST Z14-0 violates every single prediction. It's too massive by an order of magnitude, too bright by factors of 10, too enriched chemically, forming stars at rates the simulations can't sustain. This isn't a minor discrepancy, it's a fundamental breakdown of the simulation framework. The immediate response was to question whether the simulations were simply missing physics. Perhaps the feedback prescriptions are wrong, suppressing star formation too efficiently in the early universe. Maybe the star formation recipes are too conservative, not converting gas into stars fast enough. Simulation groups began tweaking parameters, adjusting efficiencies, trying to find combinations that could produce galaxies like JWST Z14-0. The problem is that these adjustments break other things. If you increase star formation efficiency to match the observed masses, you overproduce stars in low redshift galaxies. If you weaken feedback to allow more rapid growth, you can't reproduce the properties of dwarf galaxies today. The simulations are tightly constrained by decades of observations across cosmic time. There's little room to maneuver. Some researchers have focused on resolution. Maybe the simulations simply aren't capturing the relevant physics because they can't resolve the scales where star formation actually happens. In real galaxies, stars form in molecular clouds just light years across, far smaller than what even the highest resolution simulations can model. Instead, simulations use subgrid physics, simplified prescriptions that approximate processes happening below the resolution limit. If these subgrid prescriptions are wrong or incomplete, they could systematically underpredict galaxy masses and star formation rates in the early universe. Higher resolution might reveal new physical processes that accelerate galaxy formation. But pushing resolution higher is computationally expensive, and preliminary high-resolution studies haven't shown dramatic improvements in matching JWST observations. There's also the question of cosmological initial conditions. Simulations start from the density fluctuations measured in the cosmic microwave background, evolve forward according to Lambda CDM. If those initial conditions are wrong, if there were additional fluctuations on small scales not captured in the CMB, the simulations would naturally underpredict early structure formation. But modifying initial conditions is dangerous. The CMB provides extremely tight constraints on the amplitude and spectrum of primordial fluctuations. Adding extra power on small scales would need to be done in ways that don't contradict CMB observations, which severely limits the possibilities. Another approach involves reconsidering the role of baryonic physics. Most cosmological simulations focus heavily on dark matter because it dominates the mass budget and drives structure formation. Gas dynamics and star formation are treated as secondary processes happening within dark matter scaffolding. But what if baryons play a more active role in the early universe than we've assumed? Gas can cool and concentrate more efficiently than dark matter, potentially forming dense clumps that collapse rapidly into stars. If there were mechanisms allowing gas to decouple from dark matter and collapse on its own, you might get faster galaxy formation than dark matter-only predictions suggest. This baryonic collapse scenario is being explored, but it's unclear whether it can operate efficiently enough to explain JWST observations. The simulation crisis extends beyond individual galaxy properties to galaxy number counts. When you point JWST at a patch of sky and count how many galaxies you find at different brightnesses and redshifts, those counts should match simulation predictions. But the observations show more bright galaxies at high redshift than simulations predict, sometimes by significant factors. This excess of bright galaxies is particularly problematic. It's not just that individual galaxies are more massive than expected, there are too many of them. This suggests that the entire galaxy formation process was more efficient in the early universe, forming more galaxies with higher masses across the board. Some astronomers argue that the simulation crisis isn't as severe as it appears. Observational uncertainties, selection effects, and systematic errors in measuring galaxy properties could artificially inflate the tension. Maybe JWST is preferentially finding the most extreme systems, giving us a biased view of typical early galaxy properties. But as more data accumulates and analysis techniques improve, the tensions aren't going away. If anything, they're becoming more robust. The simulation crisis is real, and it's forcing theorists to confront uncomfortable possibilities about how much we really understand galaxy formation. The ultimate question is whether this crisis can be resolved within the existing paradigm or whether it requires fundamentally new physics. Can we fix the simulations by refining our prescriptions and increasing resolution? Or do we need to overhaul our entire approach to modeling cosmic structure formation? The answer will determine the future of cosmological simulation, and it will tell us whether our computers are capable of recreating the universe we observe. There's another major crisis brewing in cosmology that might be connected to the early galaxy problem, the Hubble tension. This refers to a persistent disagreement between different measurements of how fast the universe is expanding today. And surprisingly, the solution to one crisis might be linked to solving the other. The Hubble constant describes the expansion rate of the universe, how quickly galaxies are receding from us as space itself stretches. There are two main ways to measure it. The first uses the cosmic microwave background, measuring temperature fluctuations from the early universe and evolving them forward using Lambda CDM to predict today's expansion rate. This method gives a value around 67 kilometers per second per megaparsec. The second method uses direct observations of the local universe, measuring distances to galaxies using standard candles like supernovas and Cepheid variables. This cosmic distance ladder approach consistently yields a higher value, around 73 kilometers per second per megaparsec. A 9% difference might not sound dramatic, but both measurements are extremely precise with uncertainties of just 1 to 2%. The discrepancy is statistically significant, about 5 sigma in technical terms, meaning it's very unlikely to be just random error. Something is genuinely wrong, either with the measurements or with our understanding of cosmology. What does this have to do with early galaxies? The Hubble tension might indicate that the universe expanded faster in its early phases than Lambda CDM predicts. If the expansion rate was different, cosmic timescales would be different too. Structures would have more or less time to form depending on the exact expansion history. Some proposed solutions to the Hubble tension involve introducing new physics in the early universe, modifications to dark energy, additional relativistic particles, or changes to gravity itself. Many of these same modifications would also affect structure formation, potentially speeding up galaxy assembly and helping explain JWST's observations. For example, early dark energy, a component that would have accelerated expansion briefly in the early universe before fading away, has been proposed to resolve the Hubble tension. But early dark energy would also affect how quickly density perturbations grow, potentially allowing dark matter halos to form earlier and more efficiently. Alternatively, if dark matter has interactions we haven't accounted for, it could affect both the expansion rate measurements and structure formation. Self-interacting dark matter or dark matter that couples to dark radiation could modify the CMB predictions in ways that change the inferred Hubble constant while simultaneously affecting how galaxies form. The connection runs deeper. Both problems involve reconciling early universe observations with late universe measurements. The Hubble tension says the early universe, as measured by CMB, predicts different expansion than the late universe, as measured locally. The galaxy formation crisis says the early universe produced structures faster than predictions based on late universe calibrations suggest. This parallel has led some researchers to wonder if there's a common underlying cause. Maybe our model of the universe's evolution from early to late times is missing something fundamental. Perhaps Lambda CDM is an excellent approximation for both the very early universe and the recent universe, but breaks down or requires modifications during the intermediate period when structure formation was most active. Testing this hypothesis requires observations that span cosmic time, tracking how the universe evolved continuously from the Big Bang to today. JWST provides crucial data for the early universe. Other telescopes and surveys map the late universe, but the middle epochs, from redshift 2 to 6, corresponding to the era when most galaxy assembly happened, remain less well observed. Future missions will target this crucial period. The Nancy Grace Roman Space Telescope, launching later this decade, will survey large areas of sky at intermediate redshifts, providing statistics on galaxy populations during the peak epoch of cosmic star formation. Ground-based observatories are pushing to observe fainter and more distant objects to fill in the evolutionary sequence. If the Hubble tension and the early galaxy problem share a common solution, resolving one should help resolve the other. But finding that solution requires identifying which aspect of our cosmological model needs modification. Is it dark matter, dark energy, gravity itself, or something else entirely that we haven't even considered? The stakes are high. Lambda CDM has been the standard model of cosmology for decades, explaining a vast array of observations with remarkable consistency. If it's fundamentally flawed, we need to know. But if it's merely incomplete, requiring additions rather than replacement, we need to identify exactly what's missing. The connection between these two crises suggests that JWST's discoveries about early galaxies aren't just an isolated puzzle. They're part of a broader pattern of tensions in cosmology, all pointing toward the same conclusion. Something about our understanding of the universe's evolution is incomplete. And that makes the solution even more urgent to find. When established models fail to explain observations, scientists must consider alternatives. The mounting tensions in cosmology have revived interest in cosmological frameworks that differ fundamentally from Lambda CDM. While most remain speculative, they offer testable predictions that could be confirmed or ruled out by future observations. Modified gravity theories represent one class of alternatives. Einstein's general relativity has passed every test we've thrown at it in the solar system and with gravitational wave observations. But we've never tested it rigorously on cosmological scales. What if gravity behaves differently over billions of light years, or in the extreme conditions of the early universe? Some modified gravity theories can mimic dark matter's effects without requiring an unseen particle. Others modify the expansion history, potentially resolving the Hubble tension while also affecting structure formation timescales. If gravity was stronger in the early universe, structures could collapse faster, potentially explaining rapid galaxy formation without invoking exotic dark matter properties. Another alternative involves varying fundamental constants. What if the strength of gravity, the speed of light, or other physical constants weren't truly constant but changed over cosmic time? Such variations could alter how structures form and evolve. A stronger gravitational constant in the early universe would accelerate collapse. A different speed of light would change how causally connected different regions were, affecting structure formation efficiency. These ideas aren't new. They date back decades, but they've been largely set aside because Lambda CDM worked so well. Now, with multiple tensions emerging, some physicists are revisiting them with modern mathematical tools and computational power. Steady-state cosmology, once Lambda CDM's main competitor, has been thoroughly ruled out by observations. But some physicists have proposed neo-steady-state models that incorporate aspects of expansion while avoiding a singular Big Bang. These models face severe challenges explaining the cosmic microwave background, but they make different predictions about galaxy formation that might be worth testing. Then there are theories involving extra dimensions. If our universe is a four-dimensional surface embedded in a higher dimensional space, the extra dimensions could affect how gravity operates. During the early universe, when everything was compressed, extra dimensions might have played a more significant role than today, potentially accelerating structure formation. Quantum cosmology approaches suggest that quantum mechanics might play a role in the universe's earliest moments, possibly avoiding the Big Bang singularity entirely and replacing it with a quantum bounce or transition from a previous phase. These scenarios could produce different initial conditions than standard inflation, potentially seeding stronger density fluctuations that lead to faster galaxy formation. The challenge with all alternative cosmologies is that they must explain not just the new puzzling observations, but also all the successful predictions of Lambda CDM. The cosmic microwave background power spectrum, the abundance of light elements from Big Bang nucleosynthesis, the large-scale distribution of galaxies, any alternative must match or exceed Lambda CDM's performance on these well-established tests while also resolving the new tensions. Most alternatives fail this requirement. They might solve one problem while creating others. Modified gravity theories often struggle to reproduce the CMB power spectrum. Varying constant models have difficulty with nucleosynthesis. Each alternative faces its own set of challenges that have kept them on the fringe of mainstream cosmology. But the accumulating tensions are making the mainstream less comfortable. When your best theory consistently fails to predict observations in multiple independent areas, you have to at least consider that the theory itself might be wrong, not just incomplete. This doesn't mean Lambda CDM is doomed. More likely, it's an excellent approximation that needs refinement or extension, rather than wholesale replacement. The history of physics is full of theories that worked beautifully within certain domains but required modification when pushed. To extremes, Newtonian gravity served for centuries before general relativity revealed its limits. Classical mechanics worked perfectly until quantum mechanics became necessary at atomic scales. Perhaps Lambda CDM is similarly successful within its domain but breaks down in the extreme conditions of the very early universe. Distinguishing between alternatives requires observations that make different predictions. JWST is providing crucial data, but so are gravitational wave observatories, CMB experiments, and large-scale structure surveys. The convergence of evidence from multiple independent probes will ultimately determine which framework, Lambda CDM with modifications or something more radical, best describes our universe. For now, most cosmologists remain committed to Lambda CDM, viewing the tensions as problems to be solved within the existing framework rather than evidence for its failure. But the door to alternatives is opening wider than it has in decades, and if the tensions continue to grow, rather than resolve, that door might swing open completely. The universe is trying to tell us something, we just need to figure out what. JWST has only scratched the surface. The telescope launched in late 2021, and its first science observations began in mid-2022. We're less than 3 years into what's planned as a decade-long mission, possibly extending beyond. If the early results have already shaken cosmology to its foundations, what will the next 7 to 10 years reveal? The telescope's observation strategy is evolving. Early programs focused on surveying relatively small patches of sky to great depth, pushing to the highest redshifts possible. These deep fields revealed JWST 0 and the population of impossible early galaxies. But deep fields cover tiny fractions of the sky. Imagine looking at the universe through a straw. They show you what's possible, but not necessarily what's typical. Future programs will balance depth with breadth, surveying larger areas to shallower depths. This will provide better statistics on galaxy populations, revealing whether objects like JWST 0 are rare outliers or common representatives of their era. If extreme early galaxies are abundant across large sky areas, the crisis in cosmology deepens. If they're rare, concentrated in unusual environments, that provides crucial clues about what conditions enabled their formation. JWST is also pushing spectroscopy to new limits. Early observations relied heavily on imaging, taking pictures through different filters to estimate distances and properties. But spectroscopy provides far more detailed information, measuring precise redshifts, chemical compositions, star formation rates, and gas kinematics. As more galaxies receive detailed spectroscopic follow-up, we'll build a much richer picture of what early galaxies actually looked like. One key question is whether even more distant galaxies exist. JWST 0 holds the current distance record at redshift 14.32, corresponding to 290 million years after the Big Bang. But JWST can potentially detect galaxies at redshift 20 or beyond, pushing back to 200 million years or earlier. These observations would probe the very end of the Dark Ages, potentially catching the universe's first galaxies in the act of forming. Finding galaxies at even higher redshifts would make the cosmological tensions worse, not better. Each step backward in time compounds the problem of how structures formed so quickly, but it would also provide invaluable data on the transition from the Dark Ages to the epoch of galaxy formation, potentially revealing the physical processes that triggered the first star formation. JWST will also study the diversity of early galaxies in far greater detail. Not all galaxies at high redshift are massive and bright like JWST 0. There's an entire population of fainter, smaller systems that are harder to detect, but potentially more numerous. Understanding the full range of galaxy properties, from the smallest dwarfs to the most massive systems, will reveal how galaxy formation varied with environment and conditions. The telescope's near-infrared capabilities allow it to study dust in early galaxies with unprecedented detail. Dust emission reveals information about chemical enrichment, star formation buried inside clouds, and the structure of the interstellar medium. As JWST maps dust distributions across many galaxies, we'll understand how rapidly these systems were building up heavy elements and forming complex structures. Black holes represent another frontier. The little red dots that show signatures of supermassive black holes are just the beginning. JWST can detect the characteristic signatures of black hole accretion. Broad emission lines, specific spectral features, X-ray, emission detected in coordination with other observatories, mapping the population of early black holes will reveal how these objects formed and grew so rapidly, potentially solving one piece of the cosmic puzzle. JWST's GRISM spectroscopy, which captures spectra for every object in a field simultaneously, will provide enormous statistical samples of early galaxies. Instead of targeting individual objects one at a time, GRISM observations yield spectra for hundreds or thousands of galaxies in a single pointing. This will revolutionize our understanding of typical galaxy properties and their variations. The telescope will also probe the epoch of reionization more directly. By studying how neutral hydrogen absorbs light from background galaxies and quasars, JWST can map the three-dimensional structure of ionized bubbles in the early universe. This will reveal which sources drove reionization and how the process unfolded across cosmic time. Gravitational lensing offers another powerful tool. Massive galaxy clusters bend and magnify light from background galaxies, effectively turning them into natural telescopes. JWST is observing numerous lensing clusters using their magnification to study galaxies too faint and distant to see otherwise. These observations can push to even smaller, lower-mass galaxies, revealing the faint end of the early galaxy population. There's also the possibility of surprises, discoveries no one predicted. JWST's early operations revealed little red dots, objects that weren't anticipated by models. What other types of systems might be hiding in the early universe, waiting to be discovered? History suggests that new observational capabilities always reveal unexpected phenomena. Synergies with other observatories will multiply JWST's impact. Ground-based, extremely large telescopes coming online this decade will provide complementary observations studying early galaxies at different wavelengths and higher spatial resolution. Radio observatories will map neutral hydrogen. X-ray telescopes will study black holes and hot gas. The combination of multi-wavelength observations will provide a complete picture impossible from any single facility. The Nancy Grace Roman Space Telescope, launching around 2027, will complement JWST with a much wider field of view, surveying large areas of sky efficiently. Where JWST provides depth and detail, Roman will provide breadth and statistics. Together, they'll map cosmic evolution from the first galaxies through the peak epoch of star formation and into the modern universe. By the end of JWST's mission, we'll have observed thousands of early galaxies in exquisite detail. We'll know their masses, ages, chemical compositions, star formation rates, structures, and environments. We'll have traced the growth of supermassive black holes from their earliest seeds. We'll have mapped reionization across cosmic time and volume. Whether this flood of data will resolve the current tensions or deepen them remains unknown. But one thing is certain, the universe JWST reveals will be far stranger and more complex than anyone imagined when the telescope was designed decades ago. The discovery of JWST 418 and its impossible companions raises questions that transcend physics and cosmology, touching on fundamental issues about knowledge, prediction, and our place in the cosmos. For decades, cosmology seemed on the verge of completion. We had a standard model that explained the universe. From microseconds after the Big Bang to the present day, we'd measured the age of the universe to percent-level precision. We understood how structure formed, how galaxies evolved, how stars produced the elements. The remaining questions seemed like details to be filled in rather than fundamental mysteries. JWST has shattered that confidence. We're not fine-tuning a nearly complete picture. We're confronting evidence that major pieces are missing or wrong. This isn't the first time astronomy has faced such a crisis. When Copernicus displaced Earth from the center of the cosmos, when Hubble revealed galaxies beyond the Milky Way, when dark matter and dark energy emerged from observations. Each discovery forced radical reconceptualization. But there's something uniquely unsettling about the current crisis. Dark matter and dark energy, mysterious as they are, fit within our framework. We knew energy and matter existed. We just discovered new types. The early galaxy problem is different. It's not about discovering new components, but about finding that the components we know behave in ways we can't predict. This strikes at the heart of the scientific method. Science progresses by making predictions, testing them against observations, and refining theories when predictions fail. But what happens when our most carefully constructed theories, built on decades of data and tested against countless observations, systematically fail when pushed to new regimes? Some philosophers of science would say this is exactly how science should work. Bold predictions meeting potential falsification. The fact that our models are being challenged by new data is healthy, not threatening. It means we're probing genuine boundaries of knowledge rather than just confirming what we already believe. Others might see a deeper problem. If Lambda CDM can be so successful in explaining the local universe while failing so badly for the early universe, what does that say about our ability to understand cosmology at all? Are we just fitting models to available data without genuine predictive power? When we claim to understand the universe, are we actually just describing the limited range of conditions we've observed? There's also the anthropic question. We exist in a universe that produced galaxies, stars, planets, and eventually life. If galaxies form differently than our models predict, if structure emerged more quickly through processes we don't understand, does that change the probability of life existing? Could the rapid formation of early galaxies indicate that life-bearing planets formed earlier and more frequently than we've assumed, meaning the universe could be more conducive to life than our models suggested? The early galaxy crisis also highlights the limits of reductionism. Physics operates on the assumption that understanding fundamental laws allows you to predict complex phenomena. Know the laws of gravity, electromagnetism, and nuclear forces, and you should be able to predict how galaxies form. But emergence, the appearance of unexpected behaviors from the interaction of simple rules, shows that this reductionist program has limits. Galaxy formation involves gravity, fluid dynamics, magnetic fields, radiation, chemistry, and nuclear physics, all coupled together in non-linear ways across vast scales. Perhaps it's not surprising that such a complex system exhibits behaviors not obviously predictable from its components. Perhaps we've been too confident that our bottom-up approach to understanding the universe would work in all regimes. There's a practical dimension too. Billions of dollars have been invested in cosmological research based on Lambda CDM's predictions. Missions were designed, telescopes built, surveys planned, all assuming the standard model was fundamentally correct. If that foundation is shaky, how should we allocate resources going forward? Do we focus on understanding the anomalies, or do we hedge by pursuing alternative frameworks? The crisis also affects how we communicate science to the public. For years, astronomers confidently described the universe's history from Big Bang to today. Now we're saying some of that confident narrative might be wrong. This could erode trust in science, feeding skepticism about whether cosmologists really know anything. But it could also demonstrate science's strength, its willingness to change when confronted with new evidence. The human element matters too. Careers have been built on Lambda CDM. Thousands of papers have been published using its framework. Researchers have spent decades developing simulations, models, and theories based on assumptions now being questioned. There's inevitable resistance to overturning such an established paradigm, not from bad faith, but from the natural human difficulty of abandoning frameworks that have been successful. Yet that's exactly what science demands. No theory is sacred, no model is beyond questioning. When observations consistently contradict predictions, scientists must follow the evidence even when it leads to uncomfortable places. The early galaxy crisis is testing whether the cosmological community can do that, whether it can remain open to the possibility that fundamental assumptions might need revision. The resolution will profoundly shape our cosmic worldview. If Lambda CDM survives with minor modifications, our confidence in understanding the universe's broad strokes will be restored. But if major revisions are needed, new physics, modified gravity, unexpected dark matter properties, It will reveal that even our most successful cosmological theories are provisional approximations, accurate within certain domains but incomplete or incorrect beyond them. Either way, JWST Z4180 and its companions have reminded us of a crucial truth. The universe doesn't care about our theories. It is what it is. Our job is to observe, measure, question, and refine our understanding until our models match reality, no matter how many iterations that takes or how much we have to revise along the way. As observational data floods in from JWST, cosmologists face a new challenge: making sense of the overwhelming complexity. Traditional analysis methods are straining under the volume and richness of information. This has sparked a revolution in how we study the universe, with artificial intelligence and machine learning playing increasingly central roles. Galaxy formation simulations have become extraordinarily complex, tracking billions of particles and incorporating dozens of physical processes. But they're computationally expensive. A single high-resolution simulation can require millions of CPU hours on supercomputers. This limits how many variations researchers can explore. You can't simply run thousands of simulations testing different dark matter properties or feedback prescriptions. The computational cost is prohibitive. Enter machine learning. Neural networks can be trained on existing simulations to learn the relationships between initial conditions, physical parameters, and outcomes. Once trained, these networks can predict simulation results almost instantly, allowing researchers to explore vast parameter spaces that would be impossible with traditional methods. This emulation approach is revolutionizing how cosmologists test theories against observations. AI is also transforming how we analyze JWST images. Traditional techniques require astronomers to manually specify what they're looking for: galaxies with certain colors, morphologies, or brightness patterns. But machine learning algorithms can identify subtle patterns humans might miss, discovering new types of objects or recognizing features that don't fit expected categories. The little red dots, for instance, were initially identified through traditional color selection. But machine learning techniques are now being applied to find similar objects more efficiently and to classify their properties more systematically. Algorithms can process millions of sources, identifying candidates that would take humans years to find manually. Deep learning networks trained on galaxy images can measure properties like redshift, stellar mass, and star formation rate directly from multi-band photometry, bypassing traditional fitting methods. These networks often perform as well as or better than conventional techniques while being orders of magnitude faster. This allows astronomers to characterize entire populations of galaxies rather than just individual objects. But AI introduces new challenges. Neural networks are black boxes. They make predictions without explaining their reasoning. When a network classifies a galaxy as being at high redshift with high confidence but gets it wrong, it's difficult to understand why. This opacity creates tension with the scientific method's emphasis on understanding mechanisms, not just making predictions. There's also the danger of bias. If training data is incomplete or unrepresentative, algorithms can learn spurious correlations and reproduce or amplify systematic errors. When we use AI to discover objects like JWST Z4180, we need to ensure we're not inadvertently selecting only systems that look like ones we already know about, missing truly novel phenomena. Simulation-based inference represents another AI-driven approach. Instead of comparing observations to specific simulation predictions, these methods use the full ensemble of simulations to infer probability distributions for underlying parameters. Given an observed galaxy, simulation-based inference asks, what combination of physical parameters would most likely produce something like this? This approach naturally incorporates uncertainties and degeneracies that traditional methods struggle with. Generative models, AI systems that can create realistic synthetic data, offer yet another tool. By training on real galaxy images, these networks learn to generate fake galaxies that look statistically similar to real ones. Researchers can then use these synthetic galaxies to test whether analysis methods are biased or to generate training data for other algorithms. The combination of AI and massive simulations is creating a new paradigm in cosmology. Rather than having a few canonical simulations that everyone compares to, we're moving toward probabilistic frameworks that explore thousands of model variations, using AI to navigate high-dimensional parameter spaces and identify which regions are consistent with observations. This approach is particularly valuable for the early galaxy problem. The parameter space is vast. Dark matter properties, star formation efficiency, feedback strength, initial mass functions, and dozens of other factors, all potentially varying with redshift. Traditional methods can't explore this space comprehensively, but AI-driven approaches can systematically search for combinations that produce galaxies matching JWST observations. Yet this raises philosophical questions. If AI finds a parameter combination that works, but we can't explain physically why those parameters should have those values, have we really understood anything? Or have we just fit a complex function to data, no different in principle from fitting a polynomial? Scientific understanding traditionally requires not just prediction, but explanation.